This is passage 4. It's a data passage. For data passages, we're not going to read our DRC approach. Data, don't read. We're just going to quickly skim, orient ourselves to the passage. I think about 15, 20 seconds is what I would take. So I like to skim the intro paragraph. We're dealing with soil that can fail. It has something called compressive strength. Now look and we see we have 3 figures, 1, 2, and 3. Each one has compressive strength, okay, and we see that defined here, the minimum downward pressure that will cause a material to fail. Then we have wire angles on each one and percent mass 1, 2, 3. That seems to be the only difference in the 3 figures is the size of the wire changes. We see that described here briefly. Don't need to read it to know where it is. And then you get to the questions. For the questions, I want you to do a read then reread approach. You quickly read through the question and then you reread it, breaking it down step by step. We'll do the reread together. Okay, number 22, figures 1 to 3. So put your fingers on figure 1 to 3. Make sure you know where you're looking. Consider the comprehensive strengths of the mixtures containing 0.75% mass of wires. Okay, so we're looking at that line in each one, the line with the square on it. For which of the wire lengths was the comprehensive strength, so comprehensive strength, we're looking at the y-axis, greater for a wire angle of 120 degrees, we want 120 degrees to be greater than it was for a wire of 90 degrees. So where is the 120 greater than the 90? So let's just go figure by figure. So let's look at centimeter 1 first. The 120 is bigger than the 90, so we know that the 3 centimeter only is out, because we have to have the 1 centimeter wire. Let's look at figure 2. Note that is lower, the 120 is less than, so that one is out, so we can eliminate 2. Now we know the answer has to be H, but we can double check it, and we have our answer at H. Number 23, according to figures 1 to 3, for mixtures containing 1% by mass of wires bent at an angle of 90 degrees. So that's very specific spots. We have the triangle, 1%, and 90 degrees. As wire length increased, so we see the wire length here, 1 centimeter, 2 centimeter, 3 centimeters, and I just drew an arrow at the bottom to show increasing. What happens to comprehensive strength? So in the 1 centimeter is 170, 2 centimeters 180, and 3 centimeters 150. So it increases, then decreases. Choice C. Number 24, according to figures 1 to 3, we're looking for the greatest comprehensive strength that was recorded for a mixture with which of the following wire lengths, angles, and percent by mass. So let's just break them down. So the first one we have a length of 1 centimeter, an angle of 90 degrees, and a 0.5% mass. So there's that spot. Double check to make sure you're in the right place. That's about 142. The second one, 2 centimeters, 90 degrees, 1%. Is that spot, and that's about 182. 2 centimeters, 120, 0.75, and that's about 159-ish. And the last one, 3 centimeters, 120, and 1, and that's about 162. So which one is the greatest? Choice G at 182. Number 25, in figure 1, so figure 1, consider the comprehensive strength, so we're looking at comprehensive strength again, and the mixture containing 0.75% by mass of the 1 centimeter wire with an angle of 180. So make sure you're in the right spot. Would a downward pressure of 160 cause this mixture to fail? So we see the 0.75 by mass with the angle of 180 is below that 160 line, but do we know if this is going to cause it to fail? How do we know? We have to go to the reading, and it says a comprehensive strength is the minimum downward pressure that will cause the material to fail. So that means that if it's at 160, like the maximum comprehensive strength that this could withstand is about 158-ish, right? So 160 will cause it to fail. So yes, and the reason is the pressure will be greater than the strength of the mixture. So D. Number 26, according to figure 3, increasing the percent by mass of 3 centimeter wires. We're already on 3 centimeter wires. We can see that here, right? So that's our 3 centimeter wire. And we're just increasing the percent by mass. So we're just going up, right? Results in the least variation in comprehensive strength for which wire angle. So we want to know where that when we increase, there's not a lot of difference, right? There's not a lot of change. We see the least change right here. See how those are all grouped close together? And that is at 90. So our answer is 90, is where we see the least variation amongst the wires. Number 27, based on the information. This is tricky. It doesn't tell us where to look, so we're considering the entire passage. The compressive strength of soil X alone, so we're just wondering what soil X alone is, and it tells us adding wires to the soil produces a mixture of greater compressive strength than the soil alone. So when we add wires, the soil is sturdier. So what we want to know is, what is the lowest point at which the wire added compressive strength? So we have to look at all three figures and see the lowest point, and we see that in figure 3. And so when you add the 0.5 wire, it gives that about 129 is where that is. So that means soil alone will be less than 129. So your answer has to be A. Okay, reach out if you have any questions, and we'll end with a silly joke. What did the bread wear to bed? Jammies. Think about it. Have a good day.